Hello and welcome to this module number 8 of Manufacturing Systems Technology. A quick recap of the last module. We actually discussed in the last module how to perform a complex transformation process on a 3D object with respect to an orthogonal coordinate system using a concatenation of 2 translation and 1 rotation matrix. The other important aspect that I would like to cover today is that geometries can be plotted using simple lines and arcs and curves and regular shapes, but they cannot be really estimated when the topologies that you are mapping are very complex in nature. So, in this particular module I would like to look at how to represent such curves and what are the flexibilities which are available when you try to force fit a polynomial function to a certain region of the curve, so that on a very local basis I could have a proper fit of a particular region. The essence of all this is that in a computer-aided design it is always important sometimes to be able to estimate the exact topology even if it is very complex. So, instead of having one whole regular geometric feature to be able to represent the whole topology, it is a very good idea to split up the whole geometry into small synthetic curves which are again joined end to end in a manner, and so that the whole topology can be mapped in a very accurate manner. Okay. So, we now discuss the representation schemes of the curves that we have been talking about, and obviously in CAD/CAM systems usually thousands of such curves or lines are stored and manipulated, so that you can have various objects of all different complexities topologically being mapped, as in this particular case we are studying. So, when we talk about the mathematical representation of a curve, a very simple representation can be just in terms of how the coordinates are related to each other. For example, let us say if we have a straight line, we are talking about a straight line y equal to x plus 1. So, obviously there is a relationship governed between x coordinate and y coordinate of all points which will lie on that particular straight line, and that governing relationship would be y equal to x plus 1. So, it is a very simple way of looking at, just by looking at a relationship between different coordinates. Okay. This representation in mathematics is known as the non-parametric representation of describing a curve. In a similar ground, we can actually talk little differently. We can say that instead of having a xy description, let us say that there is a parameter, an extra parameter t, which is somehow a function of which actually becomes the x coordinate. So, it may be simply a relationship like x equal to t. Okay. But if supposing the curve is a nonlinear curve, when we are talking about, let us say, a parabola or some other nonlinear curve, where it can be a square of t or it can be a cube of t, there would be slight differences. In case of straight line, it may be appearing to be one and the same thing, but for different set of curves, when it comes from a linear to a nonlinear mode, it may appear to be different if you are just changing this parameters order from 1 to 2. So, what we assume is that, let us say, in the same straight line case where we talked about a non-parametric equation y equal to x plus 1, we assume x to have a parameter equal to t. Obviously, y would also have a parameter t plus 1, and so if you vary this t from some limits, let us say limit 0 to 5 or 0 to 1 or 0 to 3, simultaneously the y would also be limited within that domain. So, what I am trying to say is that instead of looking at a whole global picture of a simple x and y relationship, parametrically we are trying to associate an extra parameter which we are trying to vary locally, so that we can have an idea of the local variation of the straight line at some level. Obviously, in case of a straight line, the geometry is regular, it is linear, both those variations would be one and the same. So, the non-parametric equations can be further divided into two different cases. One is a clear cut case, which is called the explicit non-parametric form of the equation. The other is a hidden form, which is also known as implicit. I will just explain what this implicit and explicit representations in the non-parametric domain are really. So, let us look at an explicit case first of the non-parametric representation. So, let us say for a 2-dimensional general curve that we are talking about, there may be a representation V1 in a manner that the y coordinate is varying as a function of x, okay, and you are representing this by looking at V1 as x f x as the fundamental way that the coordinate frames are varying of a certain curve. Okay, so therefore, there is always a relationship between the y and the x in the manner given here y equal to fx. So it is a very clear cut relationship which is available. Okay, simultaneously for a 3-dimensional curve also you may assume a third dimension z and say that in one case it is related with respect to a function f of x, so y varies as fx, and in another coordinate z it varies as another function g of x. Again there is a clear cut relationship between the x and the y and x and the z as given in this particular example. Okay. So this is actually called an explicit or a clear definition in which you can define a particular non-parametric equation for a curve. Okay. So in the implicit case, for example, in this particular case, as you can see, there are, let us say, curves defined by all sort of variables between x1 to xn, okay, and let us say only on a 3-dimensional case we have two functions f x y z equal to 0 and g x y z equal to 0. So there is not enough clarity that how x varies with respect to y or how x varies with respect to z, or as a matter of fact how y varies with respect to z. That clarity is not available, although all the information which is necessary for assuming a sort of functional relationship is available within these two equations 1 and 2. Such a state of description of a curve would be known as a implicit representation of the non-parametric form of the curve. So what we learned so far is that how do you non-parametrically define a curve with respect to the x and y coordinates. You have a clear cut case where the y coordinate or the z coordinate as in a 3-dimensional curve is completely a function of the x coordinate, and in another case the information is around but it is in a hidden manner. You have two different functions where there is a relationship between x, y and z being indicated, and you will have to infer from that how x varies with respect to y or x varies with respect to z, or even as a matter of fact y and z, what are the variations with respect to each other. So that is the implicit way of describing the non-parametric representation of the curves. So having said that, let us look at the corresponding parametric representation. I think I had already mentioned that if I involve another extra parameter t to define all the points, for example, as you can see here the x coordinate is varying as a function of t, right. So x is varying as a function of t, some function capital X of t. Similarly, y is varying again as a function of t, and so is z varying as a function of t, and then we say that we associate a range for this t value. Let us say the t varies between some t minimum and t maximum. So what we can do is that instead of moving over the whole domain of x, y, z's, you can actually now limit the value of the t or the parameter in a manner so that on a very local basis you can describe what is going on as a relationship between x, y, z between that parametric domain varying between t minimum and t maximum. I will just come to an example problem where we show how this parametric equation can be developed. Let us say we are looking at a straight line here, for example, in the xy plane, and it is given by 2 points v1 x1 y1 and v2 x2 y2 as the two ends of the straight line. Further, we are also having a situation where we are describing a third point here vxy, which is a variable point between the v1 and v2. If we want to develop the non-parametric equations and the parametric equations of the straight line, how do we actually approach the problem? So a familiar non-parametric representation of the line can be, let us say, x2 minus x1 times of y minus y1 equals y2 minus y1 times of x minus x1. This is completely true and valid because if we look at the slope of the line from this variable point to one of the end points, it would be defined as y minus y1 by x minus x1, and so the slope does not change if you go from the local domain to the global domain of variation, where you are having both the end points. So this can be represented as y2 minus y1 by x2 minus x1. So it is completely justified in writing in this manner. Now if I were to, so this is a simple case of parametric form of representation, where I can say that y is varying with respect to x in a manner so that y2 minus y1 by x2 minus x1 times of x minus x1 plus y1. Okay. So there is a variation, there is a completely valid relationship between y and x, which is governing the whole equation or straight line, and this is a non-parametric representation. Can I now represent this in a parametric manner is the question. So let us say we want to just slightly change the way to represent this whole thing by adding a parameter here. So parametric representation. So we add a parameter t and define t in a manner so that t is equal to v1 by v1 v2. In other words, the t is described by the fraction of x length, that is x minus x1, as a part of the overall length in the x direction, x2 minus x1 of the particular straight line. Okay. And there is an equivalence between this fraction and the way that the y minus y1 would be defined with respect to the x y2 minus y1. So that is the fraction of the y, okay, from the y1 with respect to the overall length y2 minus y1. So obviously these two fractions are going to be similar if we assume a straight line like relationship. So the xy would vary linearly between the points x1 y1 and x2 y2, so that always the fraction of the x length with respect to the overall x length should be equal to the fraction of the y length with respect to the overall y length if this point varies between x1 y1 and x2 y2. Okay. So if we just look at the way that we can reassemble this equations, we can have the first equation just out of this relationship t, which is the x fraction equal to the y fraction. The first relationship x can come out to be 1 minus t x1 plus t x2, and the second relationship y can come out to be 1 minus t y1 plus t y2 from these equations. So there is a flexibility that we have now, because now if we vary, let us say put t equal to 0 here, x becomes equal to x1 and y becomes equal to y1, right, which means that at the fraction of x or y length equal to 0, the points xy are supposed to be at x1 y1, and similarly if t equal to 1, x becomes equal to x2 and y becomes equal to y2 from these relationships, which means that at fraction of x or y length equal to 1, the vxy is supposed to be at v2 x2 y2. Okay. So the points really move between the initial point and the final point corresponding to t equal to 0 and t equal to 1. What is important here for me to say is that just by merely varying this parameter between a local domain, let us say varying between 0.5 to 0.7, I can really zoom down the parametric equation to a point which is corresponding to 50% of the fraction to 70% of the fraction. Okay. So, the parameterization of the equation enables me in a way to look at a geometric object locally, provided there is a global description given by a non-parametric form of equation of the particular curve. So, this is the power of such a non-parametric representation. Now, I am going to now go to the next level and tell you that how to represent synthetic curves in a parametric and non-parametric manner, and there you will have a very good feel that a very complex topology constituted of many small synthetic curves with some relationships of interconnects between each other, how they can be traced on a profile topologically, so that they can match the exact profile into question, and that will be in the next module. Thank you.